Problem 9.29 of Sonntag. We have a compressor which is surrounded by cold R134A so that it works as an isothermal compressor. This concept is different from that of a regular compressor in which it is usually adiabatic. The inlet state is 0 degrees Celsius and 100 kilopascal and the exit state is saturated vapor. Find the specific work and the specific heat. So if we draw a compressor, this is the inlet and the exit. So it is surrounded by cold R134. This whole thing is almost submerged in cold R134A. So the inlet to the compressor and the exit are specified. So the inlet state is 0 degrees Celsius, 100 kilopascal. The exit state is given as saturated vapor. What is the specific heat transfer and the specific work? Okay, so the final state is also at 0 degrees Celsius because it is working as an isothermal compressor. For an isothermal compressor, what is the heat transfer? Heat transfer for an isothermal process, if we assume it to be reversible, would be equal to, okay, let's first write down the first law instead of writing directly so the first law tells us that for a steady state steady flow process, 0 equal to Q dot plus M dot HI minus M dot HE minus W dot. So if we divide everything by M dot, 0 equal to Q plus HI minus HE minus W. We have neglected the kinetic energy and neglected potential energy changes. Here we know what HI and HE are, but we do not know what W and Q are. There are two unknowns. So because we know that the process is an isothermal process, we can use the fact that if this process is reversible, right, if it is reversible, then Sgen equal to 0, and the second law gives us 0 equal to, so this okay, so Q by T plus SI minus SE. I have already divided everything by M dot. Okay, so the genesis of this is 0 equal to Q dot by T plus M dot SI minus M dot SE plus S dot Gen equal to 0. Because if we assume that the process is reversible, this is equal to 0, and if we divide everything by M dot, we get this equation. Using this equation, Q equal to T multiplied by SE minus SI. This is how you obtain the heat transfer, and the work done is obtained using this equation because HI and HE are known. Okay, so it's a very simple problem. So this is problem 9.29. Let's state. Let me call them as 1 and 2. Inlet state is 1 and the exit state is 2. 0 P1 is equal to 100 kilopascal. Okay, exit state T2 is equal to 0, x2 equal to 1. Okay, so Q specific heat is equal to T2 plus 273.16. Remember, we have to use Kelvin whenever we are using TDS relationships. So the TDS relationships has to be in Kelvin. Okay. So T times S2 minus S1, where S2 is equal to entropy R134A at T equal to T2, X equal to X2. Similarly, S1 is equal to entropy of R134A at T equal to T1 and P equal to P1. Using this we obtain the specific heat. Let's see how much it is. Q is equal to minus 27.78. So there is heat loss from the system. So correspondingly Q equal to, so the W, the expression for W using this equation, so W is equal to Q plus H1 minus H2. Okay, so we have to write down the expressions for H1. So it is this same state, we copy this, and H2, pardon me, is equal to enthalpy at R134A, T equal to T2 and X equal to X2. So the specific work done is minus 22.68. So the compressor requires a work equal to 22 point. The work input to the compressor is required is 22.68 kilojoule per kg. Specific work is this, the specific heat is this. Okay. So it must be remembered that for processes which are isothermal, we must, if anything else is not given, we can directly use the fact that if the process is reversible, the heat transfer is equal to TdS. That is easily derived using the second law of thermodynamics. Okay, so using the second law of thermodynamics, volume, so a reversible process implies that Sgen is 0. So the change in state from state initial to exit state is then related to the amount of heat transfer to the system, and because it's an isothermal process, we know what the temperature is. Using this we can find out the heat inputs. Okay. That is the concept. Using this second law we can find out the heat transfer, then using the first law we can find out the work done.